This topic covers reaction thermodynamics, equilibrium, and kinetics. Each one of these topics could be a class in and of itself. However, I'm going to provide the basics of each one of these, kind of reviewing things you've learned in other courses, but applying them to biochemical examples. So the learning outcomes for this particular topic are shown below. So what is thermodynamics? Thermodynamics basically describes the energy and entropy transformations in biochemical and chemical reactions. For our situation in biochemical reactions and also chemical reactions, they can be of two types: a closed system or an open system. The closed system is where energy and materials are retained within the system during any reaction or transformation. In the open system, there could be exchange of energy and materials. So under biochemical conditions, it could be either open or closed, but a cell or a living organism is in an open state because cells can import thermal energy, nutrients, chemical signals, and plus also export reaction products and energy generated as heat. So to review some basics, let's look at the three laws of thermodynamics. The first law is that energy is conserved. Energy can be converted from one form to another, but the total energy remains the same during a reaction. So mathematically, it can be expressed in the following equation. Delta E equals Q plus H, where delta E is the change in internal energy of the system. Q is the heat transferred into or out of the system, and W is the work done on or by the system. So it depends on your perspective as to whether the work is positive or negative, and the heat, whether it's being transferred into or out of the system as well. So these signs could be appropriate based on the system being considered. For biological systems, they operate at constant pressure and volume, and so therefore the first law can be described in terms of just the enthalpy component only, and so the delta E becomes delta H, where delta H is the change in enthalpy. Reactions will generally be more favorable if there is a decrease in enthalpy, in other words, a negative delta H. But a decrease in enthalpy is not the only requirement for the driving force in determining whether a reaction is going to proceed or not. But in general, delta H is negative is favorable. So let's look at the first law of thermodynamics in an example of a closed system. So when we think of delta H, we basically think of bonds being broken or formed and the heat involved in the reaction under constant pressure. So delta H can be defined as the enthalpy of the final setup of the system versus its initial setup. In other words, the final condition minus the initial condition. All of these thermodynamic terms that we're looking at, enthalpy is one of them, is considered a state function. Remember, a state function is a function that does not matter on the path to achieve. In other words, we have an initial enthalpy and a final enthalpy, but how it gets there doesn't matter. It's just a difference between the two states, a final and initial state. The path is different. The path is more of how fast does it get there, what's the mechanism to get there. That's a different question. So state function doesn't care how it gets there, it just gets there. And so we're only concerned with the initial and final states. So let's look at our example here of the melting of ice. So recall that water molecules are maximally hydrogen bonded. So every water molecule has 4 hydrogen bonds. 2 donor acceptor hydrogen bonds, and 2 acceptor donor hydrogen bonds for each water molecule. So it ends up being 4 hydrogen bonds per water molecule. And at 0 degrees, we have a transition from the solids phase to the liquid phase, the ice to water transition. In order to do this transition, we must break hydrogen bonds, because in the liquid state, each water molecule averages 3.4 hydrogen bonds per molecule, so there's less bonding interactions in liquid water versus solid water and ice form. So energy is required to break these hydrogen bonds, and it can be calculated and measured. So during this transition, it takes about 6 kilojoules per mole of enthalpy to break the bonds. That's the heat that is absorbed by the system. The formation of ice from the liquid state would require the same amount of heat to be given and removed from the liquid in order for the bonds to reform to form ice. So there's this bond breaking that liberates energy and is absorbed by the surrounding water molecules, and then there's the heat given off by the water in order to promote the formation of hydrogen bonding. So the system itself is looking at the absorption of heat or the release of heat based on bond formation. That's enthalpy. So when you break bonds, heat is absorbed. When you form bonds, heat is liberated. We can measure the heat of a reaction and experimentally in a calorimeter. So a calorimeter, you can make your own device, a simple styrofoam coffee cup. You have your reactants forming products in solution. There's a stir to agitate the system, and you have a thermometer, and you can measure that. Now experimentally, this is going to be much more isolated. You can have a highly insulated steel container. You can do all kinds of different chemical reactions, combustible reactions, to initiate certain reactions to do these measurements. But you can measure the heat that's liberated or absorbed by a system through the use of having a thermometer either in the actual reaction itself or in a surrounding water jacket that surrounds the reaction, in which the heat can be easily absorbed. So that would be your experimental system. So exothermic reactions are defined as those who give off heat. This would be an example if you form ice and your delta H is less than 0. If it's endothermic, the reaction is absorbing heat, and this is melting ice. This is breaking bonds, and the delta H is greater than 0. So these are terms that we've seen before, and I'm just reintroducing them to you here. So remember that delta H is greater than 0. You're breaking bonds. The reaction absorbs heat. Exothermic, or forming bonds. Reaction dissipates heat. The second law of thermodynamics states that systems tend to go to disorder. So this is an easier one to keep in mind about, because everything tends towards disorder. So the entropy of an isolated system will tend to increase. It'll tend to become more random or disordered. It takes energy to keep things ordered. So nature tends to go to more disorder, to more randomness. And so we refer to this term as entropy, or delta S, a measure of disorder. Delta S becomes larger as the disorder increases, or it becomes smaller as the disorder decreases, or becomes more ordered. So let's look at our example in terms of melting ice. So if we look at these two systems, ice versus liquid water, which is more disordered? The liquid water is more disordered. So we can calculate a delta S based on the entropy of the initial condition subtracted from the final condition. So anytime we do delta, it's always final minus initial, final minus initial. So in this case, the entropy of the final condition minus the initial condition, it's a state function, just like delta H is a state function. And delta S is important because it helps to determine the direction of a reaction. Often, everything wants to go to disorder. So when we look at a system, we have to consider all components and look at the system as a whole to find out if it's more disordered or more ordered. Because if you just focus on one component of the system, that component may become more ordered, but the overall system is more disordered. So therefore, as a system, there's more disorder. So you have to keep in mind of defining your system. Let's look at an example. So here's a beaker that has some dissolved sucrose in it. Sucrose are these little pink dots. And each one of these little chambers here, this is just your water. And it's kind of randomly distributed in there, okay, as sucrose has been solubilized in water. Now we're going to do a virtual experiment. We're going to double the amount of water into this beaker. That's shown here. We just double the amount of water, but we didn't mix it, okay? In reality, when you pour it in, you'll immediately have mixing occurring. But we just are doing this experimentally from a thought experiment. So we're just going to put that in there. You can imagine if we had some kind of a partition here that we could put that over, then you wouldn't have any mixing, and then we could remove the partition when we wanted a reaction to occur. So now we just put in water at the top, and you can see that now the system has become more ordered by virtue of just adding more water to the top, because now all of your sucrose molecules are confined to the lower half of the beaker. They're not randomly distributed throughout the entire volume. This is a more ordered system. The entropy has went down. If we remove the partition and let things mix, as we would do when we would add this solution of additional water to the sucrose solution, after a certain amount of time, the sucrose molecules will be redistributed, and you'd have a more disordered system in the final state. So when a system is not at equilibrium, the reaction drives it to achieve a new equilibrium. And this is based on providing, in this case, a more disordered system, more randomization of the sucrose molecules throughout the volume of that water. Going back and trying to make those sucrose molecules confined to the lower half of that beaker is never going to happen spontaneously on its own. We have to add energy. We have to do something to drive it into a more ordered state. So energy is required to make things more ordered. You must provide work in order to make something ordered. If you want to clean something, you got to put work into it. If you want to straighten stuff out, you have to put energy into it. If you just let it go, it'll automatically just go to disorder. So delta G or delta S is greater than 0. disorder increases, that's a spontaneous direction. Nature wants to go in that direction. Chemical reactions wants to go in that direction. Delta S is less than 0. The disorder decreases. The system becomes more ordered. That requires input of energy. The third law of thermodynamics is that the entropy is 0 at absolute 0 temperature. So we can have the S go to 0 if we lower the temperature enough that we're at 0 Kelvin. And that's where we stop even all vibrational motion. But with biochemical reactions, we're nowhere near this value, so this is not really a relevant law that we have to be concerned with here. And there's also a 0th law that was added later, that if two systems are in thermal equilibrium with a third system, they must be in equilibrium with each other. This law exists to support the temperature scale. In other words, how we can measure these differences are kind of shown in the temperature scale. Now we're going to introduce the concept of free energy, delta G, and how this determines the overall direction of a reaction. So delta G, the free energy, can be shown to be a combination of enthalpy and entropy by the following equation of delta G equals delta H minus T delta S. Notice that the entropy term, there's a temperature dependence on that. Just like we did for the enthalpy and entropy, the delta G can also be determined based on the difference between the final minus the initial state. So for any given biochemical reaction to go to a lower free energy, if it can, the combination of the enthalpy and the entropy must be combined to give a negative delta G value. So let's look at the example of ice melting at 10 degrees Celsius. Recall that the delta H for melting ice is a positive value. So if that's a positive value, that's going to contribute to the positive value of delta G. So let's see what we get when we consider the delta S for this process of 24.7 kilojoules per mole K, and the temperature, which is in Kelvin. That's where the K is, Kelvin. We're using the Kelvin scale, so we have to convert our degrees Celsius to Kelvin. It's not degrees Kelvin, it's Kelvin, of a factor of 273. So you take 273 plus the temperature in Celsius, add those together, and you get your temperature to the Kelvin scale. So once we determine that, we can substitute in our values to the delta G equation, and we see that we have this large positive delta H value, and we have a temperature and the delta S value here. And so let's see what happens when we multiply those and combine these two numbers. It ends up being slightly on the negative side. So when we look at this reaction, what's driving the reaction to proceed is not the enthalpic term, but the entropic term, the tendency for the system to go to more disorder. That's what's giving rise to the negative value here. If both values were equal, delta G would be 0. And it would not be going in the forward or reverse direction. It'd be basically at equilibrium. So here's a nice scale kind of giving you things to consider when you're looking at the values of free energy or the change in free energy, delta G. So if delta G equals 0, we're at equilibrium. If it's greater than 0, the reaction is not favored as written from left to right. And we can call this endergonic. If delta G is less than 0, the reaction is spontaneous as written. It's favored in the direction written, left to right. It's exergonic. So endergonic, exergonic, endothermic, exothermic. Endergonic and exergonic are delta G terms. Endothermic and exothermic are delta H terms. Don't confuse the two. So delta G's are important, and it gives us an idea of whether a chemical reaction is favored or not, and what direction it's going. And that's important when we're considering fluxes of metabolites through different biochemical pathways. And we'll see this concept throughout the course. So now let's revisit the hydrophobic interaction as it relates to thermodynamics. Recall that the hydrophobic interaction is how hydrophobic molecules interact with one another in an aqueous solution. I provided an example of a phospholipid in the previous topic, but now let's look at this interaction in terms of thermodynamic considerations. So here's a beaker filled with water, and we have our hydrophobic molecule, and we're going to plunge this hydrophobic molecule into this water. Now for this to happen, we must create a cavity for the hydrophobic molecule to be put into water. And so water molecules must hydrogen bond in such a way to make this cavity to accommodate this hydrophobic molecule. So there's a lot of ordered water molecules that surround this. It's almost ice-like in its structure. If we have two of these in solution and we want them to interact, there has to be removal of some of this ordered water so these hydrophobic portions can interact with one another without intervening water molecules to form van der Waals contacts and thus provoke hydrophobic interaction. So let us look at these two situations in terms of thermodynamics. So we have here delta G equals delta H minus T delta S. So we can look at this in terms of enthalpic and entropic terms. This process is not favorable. It's energetically not favorable for a hydrophobic molecule to go into an aqueous solution. Think of oil and water. You throw some oil on top of water, the oil just stays on the top. It doesn't go down inside. Okay? So it's not energetically favorable. Delta G is greater than 0. If we look at the enthalpic term, it's actually a favorable term. It's less than 0. Why is it favorable? Well, in this case, these water molecules are forming more hydrogen bonding than they would otherwise in this situation because they're randomly forming and breaking bonds. But here they have to be more ice-like. And so in this case, they're forming more hydrogen bonds. And so the delta H is less than 0. It's exothermic. If we look at the order of the system on the right is much more ordered. Therefore, our delta S is less than 0. And because of the temperature and this negative value here, this contributes to the overall value of delta G being greater than 0. Let's consider the case of the interaction between two of these molecules to form the hydrophobic interaction. This is actually a thermodynamically favorable process. So what's driving their reaction? Is it enthalpic or entropic? Well, if you look at the number of bonds that are formed here and formed here, and we have to break up some of this ordered water structures to form these hydrophobic interaction van der Waals contacts, we know the van der Waals forces are very weak and the hydrogen bonding here is much stronger. And so depending on these molecules, we're breaking some bonds and forming others. So our delta H could be around 0 or maybe a little on the negative side, but it's not going to be that much negative. However, when we look at the delta H perspective, there's more disorder in this part. Delta S is greater than 0. There's much more ordered water here than here. And so even though these two hydrophobic molecules have come together to form a more ordered interaction, there's much more disorder by liberation of these ordered water molecules that are hydrogen bonding here to the bulk solvent than is the order provided by bringing these two molecules together. So therefore the delta G is less than 0 and promotes the interaction. So understand the thermodynamic basis for the hydrophobic interaction. The role of water, solvent water, is the key here. Now I'm going to talk about chemical equilibria. So this will, again, is reviewing the concept of chemical equilibrium. And let's just look at a general reaction and consider some of the aspects of when we look at chemical reactions, what is that we are considering in terms of chemical equilibrium. So we'll have some kind of reaction here of reactants and products. Usually in biochemistry, it's usually two reactants to form two products, but it could be joining two molecules to form one product or taking one reactant and breaking it into two components. But let's just look at this general expression here. A plus B goes to C plus D. So if we're considering the rate of the reaction, how fast that this reaction occurs, we can look at the rate of the reaction as it's related to the concentration of A times the concentration of B times some rate constant. And so this rate constant is going to be intrinsic to the particular reaction being done. So it's going to be a specific value under certain conditions for that chemical reaction. What we can vary are the concentrations of A and B. And so if we have more A and B, the rate's going to go up. If we have less A and B, the rate's going to go down. K is a constant under the conditions of pH, temperature, pressure. Okay? If you change any of those, you're going to change the rate constant because it's not the same conditions. If we look at a chemical reaction, it's in one direction, has one arrow, but a lot of chemical reactions are reversible. So we have a forward rate and a reverse rate. So we want to consider chemical reactions as reversible. They're all basically reversible. It's just that they may be favored more in one direction than the other. It's going to be depending on these particular rate constants. So as shown before, that we have this forward rate that's in terms of this K sub 1 times the concentration of A times the concentration of B. But we also can write an expression for the rate in the reverse direction of the product of the concentration of C times the concentration of D times this K sub minus 1 for the reverse rate. Now, when we're in equilibrium, equilibrium means that the forward rate is equal to the reverse rate. There's interconversion going on. It's not like everything's just static and it stops. But things are being interconverted. It's just that those rates are equal. They're equal. And so if they're equal, then we can substitute in for these rates the equation in terms of the rate constants and the reactants and products concentrations. So for the forward rate, we'd have K1 times the concentration of A times the concentration of B equals the reverse rate, which is K minus 1 times the concentration of C times the concentration of D. We can rearrange this expression, and so we can have K sub 1 over K minus 1 equals the concentration of C times the concentration of D divided by the concentration of A times the concentration of B. Notice in our expression A plus B goes to C plus D that we have the concentration of the products over the concentration of the reactants. That is the equilibrium constant. And it can be related to the ratio of the rate constants of K sub 1 over K sub minus 1. So rate constants can be used to calculate an equilibrium constant, as well as the concentration of the products and the reactants. Another interesting point to note is that we can convert this equilibrium constant to a delta G. We can make it a thermodynamic term that we then can use to look at whether a reaction is favorable or not, or by how much. It's a very useful conversion. We can compare the ability, the potential of reactions to occur in a certain direction or under certain conditions. There's another use of free energy that we can apply to kinetics, and that's in regards to the transition state. So the delta G that we can use for determining whether a reaction is spontaneous or not, favorable or not, we can still use this concept of free energy to explain reaction rates. So let's look at the diagram below. So here's our reactants and products, and this is showing you the delta G and how we have been calculating it in our situation, where we're looking at the difference in the free energy of the reactants versus the products. And in this case, the delta G would be a negative value because the products versus the reactants would be favorable in that there are higher energy states here. And so this is a favorable delta G that's negative. We can also look at it in terms of using a concept of delta G in terms of the formation of the transition state, in terms of the chemical reaction that's being conducted, and to how difficult it is to achieve the transition state for that reaction. That's going to be proportional to the rate. So the more difficult the transition state is to achieve, the slower the rate is proportional to this amplitude of this barrier, this activation energy. And we can describe the difference between looking at the direction from left to right, and the reaction coordinate is basically a diagram showing a bond, say for example over time, how it's being energetically altered during the course of the chemistry being applied to it as part of the chemical reaction. And this is the highest point in that process, the transition state. We can look at the difference here as the activation energy, or a delta G double dagger. We can consider it in terms of free energy. So if we look at an exergonic reaction, which is the same one on the previous page, the forward rate would be in this direction, and the reverse rate would go from products to the reactants. And so the K1 that I shown before in that example of A plus B goes to C plus D would be the forward rate, is proportional to E to the minus delta G double dagger over RT. And K minus 1, the reverse rate, is proportional to E to the minus G double dagger, the same value, but we also have to overcome the delta G of the reaction itself, and that has to be added and incorporated into that reverse rate constant. So in terms of these activation energies and the delta G of the reaction itself, the forward rate has a smaller energy of activation to overcome than the reverse rate, because the reverse rate has to overcome the delta G plus the delta G double dagger. So this says it favors the forward direction, and the reaction is exergonic based on the negative delta G here. If we do the endergonic reaction, the same application of delta G double dagger and delta G apply, except the terms now have changed, where the forward direction is not favorable because the rate constant has this additional delta G to consider, whereas the reverse reaction just has to overcome the energy barrier based on the delta G double dagger. So the reverse reaction here is faster than the forward reaction. In addition, the free energy also depends on the concentrations of the reactants and products, because we can raise or lower these values based on how much reactants and products are present. So we can change these initial levels of reactants and products by changing their concentration, thus changing their forward and reverse reaction rates, and also the delta G value in these reactions, including the transition state, delta G double dagger. So we'll talk more about this as we go into enzyme kinetics, but I wanted to introduce this concept at this point that we can also look at free energies in terms of reaction rates, in terms of kinetics. So now we need to consider the types of delta G's that there are. So this is not related to the delta G double dagger and the delta G, but what we refer to as delta G at standard conditions, or delta G naught. Standard conditions are defined as 1 atmosphere of pressure and 1 molar initial concentrations of the reactants and products at 25 degrees Celsius. So consider the following reaction. A plus B goes to C plus D. In this case, I also added coefficients to each one of the products and reactants. So it could be 2 A's and 1 B to form 1 C and 1 D, for example. And so the standard free energy delta G0 can be defined for this particular reaction. If we look at the delta G of this reaction, it is the standard delta G plus RT natural log of the concentration of the products over the reactants. Okay, from basic principles, this equation has been derived. If you want to see how it's derived, you can look up a physical chemistry textbook on thermodynamics. We're going to use this equation to look at biochemical reactions and calculating delta G under different conditions like cellular conditions versus standard conditions. But we may also calculate some standard delta G's as well. So this is the relationship. R in this case is a constant. It's the gas constant. Temperature would be 25 degrees Celsius or 37 degrees Celsius. It could be something different. And Q we define as the reaction quotient, which is the concentration of the products over the reactants at some non-standard condition. Under standard conditions, though, Q's ratio is going to be 1. So if that's indeed the case, the natural log, again this is not base 10 log, but natural log of 1 is going to be 0. So delta G equals delta G0, or delta G naught at standard conditions, not equilibrium conditions. Okay? At equilibrium conditions, delta G equals 0. But if delta G is equal to standard conditions, it's called delta G naught. And the standard conditions are 1 atmosphere pressure, and all initial concentrations are at 1 molar. Okay? So this delta G then is what determines how the reaction will change to reach an equilibrium condition, a new equilibrium condition relative to the standard condition. All right, so this is the theory behind these equations. In biochemistry, we add another condition, and that is the pH. pH is important. That will affect delta G. So our standard condition in biochemistry is pH 7. So you'll see delta G naught prime, or delta G 0 prime, as the standard biochemical free energy. Okay? Recall that physiological pH is around 7, 7.4. So this is our standard pH of 7. And the pH of 7 equates to a hydronium ion concentration of 1 times 10 to the minus 7 molar. So if a reaction includes protons in it, the reference concentration is not 1 molar, but 1 times 10 to the minus 7 molar. All right? So let's look at an example here for ATP hydrolysis. And we'll have a lot of problems for you to try. There's 2 more to kind of get warmed up with, example problems at the end of this topic, and I'll go through those with you as well. But right now, let's just consider the following. ATP and water is going to form ADP plus a phosphate plus a proton. All right? So if we write the expression for the reaction quotient, it's going to be the concentration of ADP times the concentration of phosphate, in this case the monoprotonated form, plus a proton divided by the concentration of ATP times the concentration of water. All right? Delta G goes delta G 0 prime plus RT natural log of Q. Notice the following. Since the standard conditions are 1 molar, we're going to divide each of these components in the reaction quotient by their standard condition. Everything's initially 1 molar, so it's going to be divided by 1 molar, 1 molar, 1 molar. A hydronium ion concentration standard is 1 times 10 to the minus 7th molar. We're going to divide it by that. Water, by definition, and how these equations were derived and assumptions that were made, is going to be considered 1. It's not 55 molar over 1 molar. We're just going to set it water to 1, and we don't have to worry about it. That's by definition. R is the gas constant, and that's 8.314 joules per mole K. That's by definition, that's defined, that's a standard, that's a constant. Temperature will be in Kelvin, and remember that's the temperature in Celsius plus 273 degrees. So in order to take a natural log of a number, there cannot be any units. So by this convention of dividing by the standard concentration, the units cancel out. And we'll end with a unitless number. But you got to make sure when you do these problems that you convert your concentrations into molar units so that your units cancel out and you get the right value to get the right delta G. Otherwise, you'll be way off. So follow this convention in solving these problems and you'll be in good shape. If you try to make shortcuts, you'll end up having a different value for Q, and your delta G, when you calculate it, will be way off. Now we're going to look at the situation where we're at equilibrium and delta G equals 0. I kind of alluded to that earlier when we were looking at the free energy and how it relates to a value greater than 0 or less than 0, or in this case at 0, we're at equilibrium. So if we consider our model reaction and our equation related to that reaction, and delta G is equal to 0, and our Q here under these conditions will now be defined as the equilibrium constant K, or sometimes I'll put K subscript EQ, so I know it's an equilibrium constant. So under these conditions, Q is equal to K. So if we make our substitutions into this equation, with delta G is 0 and Q being K, we have delta G equals 0, which equals delta G 0, or delta G 0 prime if we had a standard conditions of pH 7, plus RT natural log of K, or delta G 0 or delta G naught equals minus RT natural log of K. And then we can solve for K in this case if we know what delta G naught is by taking the anti-natural log of both sides. And so the equilibrium constant K, or KEQ, would equal E to the minus delta G naught divided by RT. K, equilibrium constant, is calculated from the standard free energy. K is not calculated from delta G 0. This is not standard conditions. These are like cellular conditions. That's Q. K, standard conditions. Q, non-standard conditions. It's important to recognize in the problems whether you're talking about standard conditions or non-standard conditions, and what equation to use. So if you have a KEQ, you can always find a standard condition delta G. If you have a standard condition delta G, you can always find a KEQ. But if you have a non-standard delta G, you cannot find a KEQ. Keep that in mind. You must have a standard conditions in order to find the equilibrium constant. So let's look at this example from the textbook. So this is the second step of glycolysis, where you have the conversion of glucose 6-phosphate to fructose 6-phosphate, and the delta G naught, standard conditions, is 1.7 kilojoules per mole. So this is a positive value. This reaction is endergonic. And so in terms of delta G, not standard condition, it equals the standard conditions plus RT natural log. In this case, Q is equal to 1. And so the delta G naught is equal to the delta G in this case, which is greater than 0, which is an endergonic reaction. So at equilibrium, which is what we're considering here, the reaction favors the formation of glucose 6-phosphate at 25 degrees Celsius in terms of the concentration. Okay, remember, equilibrium conditions, the forward and reverse rates are the same, but you may have more of one product or reactant. Maybe doesn't necessarily have to be equal. The rates are equal, but the concentration of the reactants and products at equilibrium do not have to be equal. So let's see how they're related based on the delta G standard condition value as it relates to the equilibrium constant. So we can calculate K based on the previous equation that was shown in the former slide of minus delta G standard conditions divided by RT. Make the appropriate substitutions. Just make sure your units cancel. You convert kilojoules to joules, or you can convert joules to kilojoules. When I do my problems, I like to take the gas constant here and make it 8.314 times 10 to minus 3 kilojoules per mole K. The book may like to show an example where it turns anything into joules. Doesn't matter, just make sure your units cancel so that this exponent is unitless. Don't forget the negative sign here. So if your delta G is negative here, a negative is a positive. In this case, this is positive, so this exponent will be negative. When you do the calculation, you end up with 0.504. In this case, 0.5. So the dissociation constant is 0.5 for the concentration of the products over the reactants at equilibrium. Since the equilibrium constant is less than 1, there is more of glucose 6-phosphate there is a fructose 6-phosphate at equilibrium in a 1:2 ratio. The rates in the forward and reverse direction are the same. This is the condition that exists at equilibrium. Standard delta G values. So let us now consider what's actually happening in the cell with this particular reaction. So during glycolysis, the formation of fructose 6-phosphate is favored because the reaction is not at equilibrium. So here's our equation in terms of delta G equals delta G naught plus RT natural log of Q. And we can substitute in Q for the concentration of fructose 6-phosphate over glucose 6-phosphate. Again, these are not at equilibrium conditions. We can make a substitution here for delta G naught with minus RT natural log of K, the equilibrium constant. And when we do that, we can simplify this equation of delta G in terms of Q and K, where delta G equals RT natural log of Q over K. So in the case of where Q equals K, then the natural log of 1 is 0, so delta G equals 0. Okay, so we can look at the interplay between Q and K, and maybe this will be a little easier to understand the reaction as well, in terms of the directionality that can change under different reaction quotients under cellular conditions. So if fructose 6-phosphate is low because it's being used up rapidly in the next step of glycolysis, that is to say that it's just not sitting here and being converted back to glucose 6-phosphate, but being used by another enzyme in the next step in glycolysis, the concentration, the steady state concentration based on this reaction rate, and the subsequent reaction rate that uses this as a reactant will alter its concentration. So this ratio between glucose 6-phosphate and fructose 6-phosphate can be less than the equilibrium constant if we have less of this fructose 6-phosphate present compared to the equilibrium condition. That's only the interconversion between these two species. So in that case, Q is less than K, and so this ratio of Q over K is going to be small, and so that's going to allow delta G to be negative, since Q over K is less than 1, because Q is less than K. So in this case, the reaction would be exergonic, favoring the formation of fructose 6-phosphate under the conditions in a cell in which glycolysis is occurring. So there's this interplay with the reaction quotient being different than the equilibrium constant, because the concentrations are different. Here's a slide looking at the different conditions and interplay between Q and K. So this is the delta G of the reaction. We got rid of the standard delta G by incorporating this ratio between Q and K. So if Q is less than K, this value here is going to be less than 1, and therefore delta G is going to be less than 0, exergonic, varying the forward direction. If Q is greater than K, then this value is going to be greater than 1. Delta G is going to be greater than 0. Reaction is endergonic, which favors the reverse reaction. And if Q equals K, we're at equilibrium. So natural log of 1 is 0, delta G equals 0. Although it should be noted that there may be more reactants or products depending on what that K value actually is for that particular reaction. That's exactly what we saw with the example of glucose 6-phosphate being converted to fructose 6-phosphate. Important takeaway message here is that reactions that are part of pathways are typically not at equilibrium. The metabolic flux through a system of a cell, there's a lot of biochemical processes going on. They are usually not at equilibrium. Concentrations of metabolites may be at a steady state, but they're not at what we define as equilibrium conditions, where the rates of the forward and reverse reactions are going to necessarily be the same because of the partitioning of reactants and products through other enzymes. Second take-home message is that the direction of the reaction depends on Q, not K. So K doesn't tell us what direction the reaction is going to go, because that's at equilibrium. And equilibrium means that the forward and reverse reactions are the same. It's just that if we want to drive the reaction away from equilibrium under non-equilibrium conditions, then Q is going to be the deciding factor. The concentrations under non-equilibrium conditions that would dictate what that delta G is. So a positive delta G standard condition does not mean that delta G under cellular conditions will be positive. It could be, it may be negative. It depends on the concentrations that are of the given system at that time. So the direction of the reaction will depend on Q, not K, in terms of the non-standard delta G. So the best way to get a handle on understanding free energy calculations for biochemical reactions to actually do problems. So I have a couple example problems attached at the end of this particular topic. This is example problem 1, where we have the conversion of glucose 1-phosphate to glucose 6-phosphate. And what's provided here are the free energy phosphate transfer potentials for each one of these molecules, glucose 1-phosphate and glucose 6-phosphate. And you're asked to A, calculate the equilibrium constant for this reaction at 25 degrees Celsius, and then consider if a mixture were prepared with different concentrations, what would be the thermodynamically favored direction for the reaction. So anytime you encounter one of these problems, you want to consider, are we talking about a standard condition, or is it a non-standard condition, not at equilibrium? Okay, so when you determine that, then you know what equations to use. So I'm going to let you work on this yourself. I will post a solution to this problem, and you can watch the video later to see how I worked it out and see how well you did yourself. And then you can use these strategies to help you work on the problem sets and the mastering problems as well. Example problem 2 has a similar reaction we saw in this topic presentation of A plus B goes to C plus D. And here's a delta G 0 prime value of 4.1 kilojoules per mole. And if this reaction were to occur at 37 degrees Celsius with the following steady state concentrations of A, B, C, and D, calculate delta G and determine if the reaction is endergonic or exergonic. Again, the same strategies apply. Are we considering free energy calculations for standard conditions or at non-standard, non-equilibrium conditions? Then picking the appropriate strategy to solve for that particular delta G. So give this one a try, and you got to watch out for the units to make sure they cancel. So be careful when you do those. And again, the solution to this problem will also be posted with a video explanation going through the problem step by step and showing you strategies that will help you work on problem sets and mastering assignments. So again, make sure you spend time trying to understand thermodynamics and doing these calculations, because you will see problems on the exam that you'll have to work out. And so you have to know the proper strategies to attack these problems. And once you do a number of them, it becomes pretty clear of what strategy to use.